Today we're carrying on with material from yesterday, learning a bit more about malloc and about structs. We're hopefully going to take a bit easy today before moving on to our next big topic probably tomorrow, which is a new, exciting, slightly more complex data structure that uses pointers and malloc and all the things that we've got this far to give us some pretty powerful new techniques. So let's start with learning a little bit more about malloc, playing around with it, seeing a little bit of code, and this will enable us to then move to our advanced data structure. Here we have a basic snippet of using malloc on its own just to create a valid pointer. So up the top we have a pointer, just calling it t-pointer, and it's of type t. Now type t is type deft to something. We don't know what it is. But in this case, it doesn't really matter because the whole idea of using a type def is to abstract away some of the details that we might want to switch out later. So if this was a student t, we could type def our type t to be student t so that they're the same thing. Now later, if we want to do a class t, we could do the same thing, or a subject t, and make our type t point to a subject. Anyway, moving on from that, putting it in the back of our minds because we're abstracting it away, let's create a pointer of that type. So create a type t pointer, and then we have here our malloc statement, and we want to create n pointers. We want to make room for n of these objects. So let's say we want 50. We would set n to 50, so let's make an array of 50 of these type t objects. And then we're going to malloc n times the size of star t pointer now. So here we've got to be careful to distinguish between the creating n pointers to type t objects or creating space for n type t objects themselves. Now remember there's a difference. If a pointer is just going to be like 8 bytes or 16 bytes depending on the size of our machine, and a type t object might be even larger than that. So if we think back to our really large Linux structure yesterday, our task struct was super big. It might have been like 100 bytes. So if we want to make room for 100 of those, then we have to be careful that we're taking the size of that type and not the size of that pointer type. And what we're doing here is we're dereferencing our t pointer over there, which gives us back a type t object. And so we're getting the size of the type t object, so we're making n of those type t objects as opposed to n of the type t pointers. I see a lot of confused faces. They're questions. So now that I've created n of the type t, room for the n of the type t objects, I'm now going to check if that malloc actually succeeded. So there I'm going to check if malloc produced a null pointer, and if we know if it didn't produce a null pointer, then the malloc call has succeeded. But otherwise we're going to print that no memory is available, and then we have an assert statement there just to be super sure that it is in fact non-null. You probably don't actually need that in your code. You can do one of these two things. The assert statement is probably a less clean way, but it will ensure that your program immediately terminates and throws a big error that you can see. Otherwise, if we've succeeded, then we can do a whole bunch of stuff with our t-pointer or any of the objects in the array of t-pointer objects. Now remember that an array is really just pointing to a block of memory with the right size chunks. So if we've said that our pointer points to type t objects, then if I start using the array notation and ask for the first object, it will automatically skip that many bytes on to make sure that I actually get to the next object automatically. At the end, once I've finished doing stuff, I want to free my t-pointer because remember we don't want a memory leak. And then what I do is I set the t-pointer to null because free doesn't automatically actually change what's at the pointer. The pointer is still, it's just an integer value. It points to a memory address somewhere. And so that memory address might be a valid address or it might be an invalid address. We know it's invalid now because we have freed it. However, our program doesn't automatically know that. We know it because we're keeping track of it. But the way to tell the program for future that this is no longer a valid pointer is to set it null manually. And then we know that if we go back to our check and we want to check if this is a valid location, if we do another assert later and assert that the t-pointer is valid memory, that it's not 0, our program will crash. So this is our way of protecting ourselves by indicating for the rest of our program that this pointer is finished, that memory there is no longer valid for use. So in the context of a more realistic object, let's try it with plane seats and planes. So we're going to allocate this time size of seat t multiplied by the number of seats on our particular plane. And let's make this plane a Boeing 747. It's going to be a Qantas one. This is going to be the carrier. It's just another struct. We have 174 seats, and we're going to these should have been probably in the slight other order. There is an error here because I'm actually declaring the plane after I've used the plane over here. And this doesn't work. You can't reassign the elements of a struct after the fact. So you can't allocate either. Let me type this out. It's going to be easier to explain. So let's switch over here. Let's have our plane T. What am I going to call this plane T? I'll call it QF101. That's a Qantas flight. So at the time that I first declare it, I can declare it either this way or I can put all the details in there. And I forget what I said. I said it was a Boeing 747, a Qantas one, 174 seats. And then I have an object there, plane seats. But we haven't made plane seats yet in this bit of code yet, so this isn't going to work. What I could do is I could create QF101. Then what I could do is do QF101 dot name equals Boeing 747. Then I could do QF101 dot carrier equals Qantas. QF101 dot let's do dot capacity equals 174. But I don't have a seats object yet, so if I want to actually keep track of who's sitting in the individual seats, I'm going to have to make those seats. So like I had on my previous slide, I'm now going to make a collection of seats. Malloc, size of seat T, because I need to know how large a seat is to allocate enough memory for all of them. And now I can do QF101.capacity, and that'll make enough seats. Now I can go back to QF101 and assign the seats to the plane seats array or chunk of memory that I've just created. Remember, an array is really the same thing as a pointer to a chunk of memory with some syntactic sugar. So now what I could do is I could do QF101.seats0, and that would give me the first seat. Or I could do QF seats 1, or I could do QF101 seats 2. However, we still have an issue. Thanks to some scheduling constraints, we are now having to move to a larger plane. So let's see what this would do to our code. If I now want to access the 200th seat, it's still the same flight number, we've just moved to a different plane. Let me do this on the previous line. I want to access the 200th seat, and I want to set the passenger to be passenger number 875. Now, is this going to work? And if not, why not? And that should give you a hint of what the answer to the first part is. Yeah?
Is it because the capacity only has 174 seats?
Yeah, I've only allocated room for 174 seats of the plane, so I'm accessing part of an array that doesn't exist, that we don't have permission for, and this could crash our program or it will result in bad behavior. We don't know what will happen. So what I'd ideally like to do is I'd like to change the number of seats. So we should think up a way that we could do this. So one way is we could create an entirely new plane. So we could do something like this, where I have a new plane and I have allocated a new plane seats here. I've made a new version of plane seats that has room. But this still doesn't seem like an ideal solution. Is there a way for us to transfer the information on all the old passengers and just add the new seats into our object? There's got to be some way of doing it better. So option 0 that we just tried was to use the extra memory at the end of the 174 seats because the computer has more memory, it's just waiting there for us. But as we just discussed, that isn't going to work because that memory doesn't belong to us. Even though it might still be on the heap and the heap might still have room, we haven't been given permission by the operating system to take that memory, and so who knows what's there. So we could try that, and then what we'd do is we would copy 5 into the new seat. And this will give us a segfault. We're accessing a seat that we don't have permission to do. So the first thing we could do that might actually work is we could create a whole bunch of new seats. So we had our old seats array, let's make a new seats array, and let's manually copy all of the passengers in from the old seats into the new seats. So our first line over here is just allocating a new array. We're creating it for the new plane's number of seats. And then we'll loop over all of the seats in the old plane and individually copy each seat. And copy seat is just a function that I've made. If we were going to write out our copy seat function on here, it would look something like this. Copy seat, seat T, seat 1, and then seat T, seat 2. Let's make those pointers. And then it would look, maybe the computer will automatically, yeah, something like that. Thanks to the magic of AI, I didn't even have to type all of that out. It just automatically filled in what it thought would be a reasonable seat copying function. So let's actually change this to be a little clearer. I'm going to rewrite it. Let's make that destination source. So we're copying everything that was in the source seat into the destination seat. So this time the AI has actually done something a little better here. It's now making a check to double check that both our pointers are valid, and this is actually a better thing to do. And then so it copies what was in the original seat into the destination seat. It's copying the price of the original seat into the destination seat and the status of the seat into that one. So it would look something like that. And then once we're done copying all the old seats into the new seats, then we would free it. Yes, Belle?
Why are you not passing the result of that, Mel?
Why am I not passing the result of? Your compiler will probably complain if you don't cast it, but it will work because it is just a number at the end of the day. Yeah. So the compiler will automatically convert the type for you and will likely come up with a warning like type on the left-hand side does not match type on the right-hand side. Any other questions on this one so far? No? We're all good? Now, this was a little tedious and we had to do a fair bit of work. So our C standard library has a built-in function to make things a little easier for us. And this is a function called realloc. And realloc looks roughly like this. So we set plane seats on the left, our destination for the new memory, and then we are going to give it what the amount of memory that we want it to grow by. So let's look at realloc in our man pages. So realloc takes 2 arguments, and so I will fix this one up really quickly. I'll put that back. Realloc takes 2 arguments. It takes a pointer to the thing that we want to expand or change the size of, and then it takes as the second argument the new size. And if we look over here, the realloc function tries to change the size of the allocation pointed to by pointer to size and returns pointer. If there is not enough room, it creates a new allocation, copies as much of the old data pointed to by pointer as will fit, frees the old allocation, and returns a pointer to the allocated memory. So this is pretty much exactly what we were doing manually, just a new, we have a convenience function from the library that allows us to do it much more quickly and much more easily. Even better, the first thing it tries to do is just to expand the size of the original allocation. So if it is possible to do it without copying, it will. And if it's not possible because the memory there isn't memory in that particular spot available, then what it will do is it'll create a new larger spot, copy everything over, and free the old one. So it saves you all of that hassle. So there is our corrected slide that has that extra argument there now. So we have the old plain seats is our pointer, and then we have the size of a seat t multiplied by the number of seats in the new plane. And so this will do the same thing as our slide before, just a little more conveniently. So this leads to the question in general, by how much should we increase allocations? So let's move away from the plane example and go back to our class example. So in our class, we have students joining the class and leaving the class all the time during the start of semester. So one day I might check our enrollments and we'll be at 455, and the next day it might be 456, and then 454. So let's say that we start our class at 455, and I get a new student who shows up to the class, and I'm managing my class using a C program. What do you think I should do in terms of allocating more memory? How much more memory should I allocate? Who wants to answer this one? I've already answered today. Yeah. What do you think? What was your name? Shanila.
Can I just do it student per student?
So when a new student comes in, I could increase the allocation by one student. That would make some sense. Any other ideas? Michael.
If you don't want to use or reallocate in one, you don't want to use realloc too many times, you might want to wait, might increase by a little bit more so that you can account for maybe a couple more students maybe. So instead of doing it by one, like 5.
Why might I not want to do realloc lots of times?
It's to be, I'm assuming it'd be pretty expensive to execute over and over.
So if we look back to our slide before that had what was actually happening under the hood of realloc, where I go through a loop, go through all the students in the class or all the seats in the plane and copy them over, this seems like something that might take a lot of time, especially as my class size gets large. So let's imagine we're back in FOC, we have 1,000 students in the class, and I have 1,001 student, the 1,001st student joins, so I copy the records for all the 1,000 students, and I add one at the end. And then I get another student the next day. And so I copy all the students into a new one, and now I have room for 1,002, and I add the new student on. And that's gonna take a lot of work for the computer, more than might be necessary. And you know, memory is pretty cheap. I have a 1 terabyte hard drive that I can buy for like $50. I can buy 128 gig of RAM for $100 or so. So adding like space for an extra 100 students probably doesn't cost me very much. And assuming that I'm going to be adding students or removing students fairly frequently, it makes more sense to do a memory computation trade-off here, where I'm going to waste a little bit more memory for students that haven't shown up yet, in return for not having to do this computation where I copy all the students over and over. So a very common pattern that you'll see when it actually comes to deciding how much we do grow our allocations by is growing our allocations by a factor of 2. So every time that you run out of room, double the amount of space that you are taking up. Now, there are situations in which this strategy may not be so intelligent, but it does help to amortize, which means to break down the cost over the whole series of operations that you're doing. So it means that you're going to, assuming that your data is not exponentially growing itself, you'll be pretty certain that if you keep doubling, you'll need only a logarithmic number of doublings to encompass the entire size of all the data that you expect to receive. If your data is growing exponentially, then you've got other problems and might need to think very carefully about how you're managing it. So realloc is expensive, and it's often better to use a little bit more memory going to waste than spending all that extra time. So here's another quiz. What is the value of plain seats after this code? I want someone who I've never spoken to before. If I've never spoken to you, put up your hand. I know there are a bunch of you here. Yeah, what was your name? Nick. Okay, so what is going to end up in plain seats at the end here? So what does malloc do? Does it return the amount of memory allocated? So we've told it how much memory we want it to allocate, so we probably already know that. What's malloc doing for us? Yeah, it's finding some memory for us and giving it back. And so if we want to know what memory it's found, what do we need? How does malloc tell us where the memory is? Malloc has to return for us the address of that memory that it's found. And so the result of plain seats here is going to be the memory address that malloc has found for us that's large enough. And what we're doing, as Belle pointed out that I missed before, is I now have a cast here just to say, you know, this random chunk of memory, treat this as a random chunk of memory for seat t's. And that's all that cast, that bit in the brackets is doing, is it's saying use what malloc has given you, which is an address, and use that specifically to point to seat t's. And what about plain seats after this code? So Nick as well, now we've gotten the value of the address back from malloc, and now I've run free plain seats. Now what's the value of free plain seats?
It will still be the same until you make it null, right?
Yeah, exactly. So plain seats here is still the same address. It's just that that address no longer belongs to us. So what malloc and free are doing is giving us ownership over chunks of memory, even though that memory always existed. So if we set plain seats to that same address before using malloc, it'd have the same value after malloc. The difference would be that the operating system would have given us permission to use that memory. However, because we don't know ahead of time where the operating system, which chunk it's going to give us, you have to use malloc to get that address and not just to give you permission. So it's a trap. The pointer still contains the address. If you were then to access it, that would be a segfault. This is called a use after free bug because you're using memory after you've already freed it. So after you free a pointer, always remember to set it to null. And I think nowadays compilers can pick this up a few times. Sometimes they'll notice for you, which can be an additional help in noticing that you've done this. So let's go back to our computer over here, and let's check out some other code that does some mallocs. Let's look at some malloc code over here. Now all this one is going to do, we're going to have an array of pointers to characters. So each item in the array will be a pointer, and we know that because this would be an array of characters. So if we add a star, this is an array of pointers to characters. And so each element in the array is going to point to a chunk of memory, and at those chunks of memory, we will then store characters. We're going to start at 10, and we're going to try and fill the array with valid pointers. So at each index of the array, we are going to call malloc with n bytes, and each time this loop finishes, we're going to multiply n bytes by 10,000. So we're going to allocate progressively larger and larger and larger chunks of memory and see what the computer does. So let's see. Let's give it a run. Now one might anticipate my computer will get unhappy fast, and that is indeed what happens. So it allocates 10 bytes successfully. It allocates 100,000 bytes successfully. It allocates however many bytes this is, and however many bytes that is, and then fails once I ask for memory outside the scope of what my computer can handle. Now there are a couple of gotchas here. So my computer only has, what's this got? I think I've got 32 gigabytes of memory. So that's 32 by gigabytes, and that should be the number of total bytes that I've got in my computer. Gigabytes, megabytes. kilobytes, that's what I forgot, yeah. Kilobytes. So there is the total number of bytes in my computer, and if we look, let's paste this in, we'll see that I actually exceeded the number of bytes in my computer before malloc failed. So this gives us a little bit of a puzzle. Malloc is seemingly able to allocate more memory than my computer actually has. And so what the computer is actually doing is it's allocating me the ability to use it's giving me permission to use more memory than my system actually has, but that doesn't mean that that memory will actually work if I try and access all of it. And this is one of the hidden traps here. So for small allocations, you're pretty much guaranteed that the computer does actually have that memory for you to use. And what will happen if you start using memory outside those bounds, the computer will start swapping things out of its main memory, out of the RAM. So I have 32 gigabytes of RAM. It'll take things out of RAM and start putting them on my hard drive. And then when I want to access some of the memory that it's put on my hard drive, it'll take the memory from my hard drive and put it back in the RAM and take something else out of RAM. But what do we know about the difference between a computer's RAM and a computer's hard drive? Which is the faster one? The RAM. And does anyone have an idea how much faster it is? Yeah, roughly 3 orders of magnitude. So if it takes 100 milliseconds for something to be read from RAM, that's probably too much. But if it takes 100 milliseconds to read something from RAM, it'll take multiple seconds to read it from hard disk. Which means that once you get to this point where you've used up more memory than is in your computer's RAM, the whole computer will start slowing down, because every time you want to add something into your memory, it's going to start swapping things in and out and in and out. Now, I think the actual seek time for a hard drive is probably still under a second. Does that sound about right? Half a second, I think, is roughly accurate. It depends whether you're using a solid-state drive or a magnetic hard drive, which means our memory accesses are probably going to be from RAM, are going to be in the low millisecond range, which I think is accurate, but you can look that up and correct me after. But the main point of the story here is that malloc is a pretty flexible tool, but just using malloc doesn't necessarily guarantee that your computer is going to work or run quickly, because it does have these quirks. However, eventually, even malloc, even with this strategy of swapping things out to the hard drive, is going to fail. It's going to cap you at some point. Now, there's another limit that we also haven't talked about, and these are the limits to our stack size and the limits to our heap size. Now, if you remember, our memory is divided up for our program into the stack, which is every time you create a variable in a function, it goes into the stack, and then we have the heap that we can use, that we can access by using malloc. Now, why might it be a bad idea for a program to be able to use as much heap space as it likes, or as much stack space? Rose, what do you think? Nah? So how many programs do you have running on your computer right now? What was that? A few. Let's say you have 10 programs. And let's say I make my program, I start running this program here on the computer, and I start using up as much stack space and as much heap space as I'd like. What does that mean for the rest of the programs on your computer? Yeah, they're not going to be very happy programs. And the whole job of our operating system is to make sure that each program gets its fair shot at using the computer. Because there are some really important programs running on here, like the one that changes what's displayed on the screen when I move my mouse. If that program stops working, then we're in a lot of trouble. And so on top of the restrictions imposed by the actual size of memory on my computer, the operating system is as well going to put limits on how many variables I can make in the stack, and oftentimes how much heap space I can use as well. And so another potential point of failure, if you're just creating memory and memory and memory and memory, is that you'll run over the limits that your operating system imposes. If you want to learn more about that, I think we offer some content on it in our third-year computer systems course, and otherwise you're always welcome to read online. Which takes us back a bit to managing your malloc. So we've got this powerful tool that allows us to use and semi-abuse our computer's memory, but we need to be responsible for it. So there are a few things that we should always be doing. The first is to check if malloc succeeded, because as we saw, it can fail. The second is to not assume that you know the size of a type, because on a 32-bit machine, how large is an integer? I just said it. 32 bits. On a 64-bit machine, 64 bits. So if you hard code the size of an integer and say, I want my array to have 8 bytes by 16, so allocating room for 16 ints, and then you move your code and try running it on a 64-bit machine, it's not going to work. You're not going to have allocated enough memory. So this is why you have to remember to use size of. Next, don't forget to free the memory you allocated. We don't want any of you memory leaking, and then set the pointer to null. And the return type of malloc is void star. It's a pointer to, I don't know what type of object. And so it's always best to add a cast. As Bell reminded us, the compiler can implicitly do this cast for you, but you're better off if you tell the compiler and tell the program what the object is that you're actually casting it to. So add that cast when you use malloc. Now we have two other examples for today. We have our size of demo over here. And I'm just going to go ahead and display on my particular computer. Now remember, this is dependent on the particular computer and operating system you're using, what the size of all these different types are. And you'll notice in my printf, I've used %ZU, that is to particularly display the output type of size of. That's a special built-in feature into printf, where %Z will give you a size typed variable, and U makes it unsigned. So let's give this one a run. I can see the size of a char is 1 byte, an int is 4 bytes, a float is 4, a double is 8, etc., etc. Okay, and we have one more demo in this lot. And this is building on our getWords function, which I believe Junjong would have showed you. Is that right? Showed you a version of getWords? Yes? No? Yes. Okay. So we're doing the same thing that we did before. We're breaking up the input into a sequence of words, except now we want to be able to deal with really large files such that we don't have to set ahead of time how many words we're actually going to have capacity for. If you remember in the prior version of getWords that you would have seen, we've hard-coded a cap. So we said maybe look for 1,024 distinct words. If you get a new word after that, throw it away. Because we don't know how many words we're going to get. And before we had malloc, we'd have to fix the size of our arrays. And so what we're going to do now is we're going to allow us to expand arbitrarily large as we get more words in. So you could keep growing the size of your text and still have room for more distinct words. So this is roughly as before, except now we have a pointer to a pointer, which is going to be a list of words. And so this is now where we see part of the power of this is if we know that a char star is a string, so that's a pointer to a series of characters, then we can have a char star star, which is an array of pointers to characters, which is the same thing as saying an array of strings. We're going to we're going to allocate all our variables initially. The number of words we've seen thus far is 0, etc., etc. And we're just going to make sure that our initial allocation has succeeded. So we're going to set an initial size for how many words we're going to start with. We'll have room for 100 words to begin with. If we get more words, then we will grow the size of our array through realloc. So we have made an array of strings. How large is our array of strings? It is 100 words. It has room for 100 words. And each word is a string. And so the type that we're getting size of is we're getting the type of a character pointer. Because a character pointer is a string, and we want an array of strings. So now we have our while loop as before. We're just checking to see are we actually able to get a word, and we'll look at the getWord function again in a second. If we get another word, count that we've gotten another word. Linear search through our distinct array. So we have all words, which is our array of all the distinct words that we've seen so far. And at each index, check if the word we just read in, one word, is equal to the word that we're looking at in the array of all words. So if we're going through our array, looking at every possible word that we've read in so far, and we don't find the new word in that array, then we know it's a new word. So if it's not in the words that we've already seen, by definition it's new. So if still not found, then there's a new word. And this is where our logic gets a little bit hairy, because we have to check now, is there actually room in our array for the new word that we just found? So our first condition, if the number of words that we have in the array already is equal to the current size, then we don't have words. We've exactly filled up our array. So what we do is we double our current size, and then we call realloc with that new size. So we're reallocating all words into an array that is twice as large as it was before, because we've just doubled current size. And we have our check just to make sure that our reallocation succeeded. At this point, we know for sure that there's room, because if there wasn't room, we've just made it bigger, and if there was room, then we didn't have to worry in the first place. So go to the last element in the array of all the distinct words so far, and we know the last place, the next free place in the array is equal to num distinct, because if we've seen 10 words, that means index 10 in the array is free because our indices start at 0. So if we've seen one word, slot 1 in the array is free because the one word is in slot 0. So now we need to make room at that slot for in that slot we're going to put a pointer. But that pointer has to point to a place that has enough room for the new word. So what we're going to do is we are going to access that pointer at num distinct and make it set its value to be a new pointer. And how much space should that pointer point to? That pointer should point to enough space for the length of the new word that we've just read in, plus 1. Why do we have the plus 1, Rachel? If I tell you that the string hello has 5 letters in it, how many spaces do I need to store that string in memory? Hello, 5 letters. So how large does an array need to be that stores hello? 5? What's at the end of every string? A null byte. So how many spaces do I need? Hello, 6. So that's where my plus 1 comes from. My plus 1 is the length, the number of letters in the word, plus 1 space for the null byte. I've now malloced enough space, so I've created space in memory for my new word, and so I get an address back, and where am I going to store this address? I'm going to store this address in my list of all words in the last slot there. So what I've done is I've gotten permission from the operating system to store the new word, and then I've taken the address that the operating system's given me, and I've put that address in my array of all the distinct words so far. I want to check if it succeeded, but given that it succeeded at this point, I can now copy the new word that I've gotten in, and I can increment the number of words that I've seen thus far and where that free slot in the array is. At the end of the day, then I can just print the number of words that I've written and then go through all the words and print them out one by one. That's code you've seen before. So our exit if null is just checking, that's our check to make sure the malloc succeeded. And I'm also including getWord.c, which and we're going to feed in Moby Dick. So it's taking a little time to run. And we could fit in 19,472 distinct words without having to know ahead of time how many distinct words there were in Moby Dick. Our code works. This is a great success. But some of you might be feeling a little sad because our code is starting to get complicated. You're now having to keep track of every place that you've allocated memory. In this case, we both allocated memory for the pointers themselves. For each distinct word, we had to make a new pointer. And then for each of the words, we also had to assign a chunk of memory for the word themselves. So we had to dynamically have room for new words, so expanding the size of our array as the number of words there increased. And for each word, we also needed space for those words themselves. Now, this is getting difficult. How am I going to remember to actually free all this memory? So there are a couple of answers, but one of the best answers is to just move a step beyond what the compiler does and move to more complete static analysis. So one of the things the compiler does is it has a whole bunch of clever rules about how to detect things that go wrong. But the compiler doesn't do everything that's possible to do in terms of checking. We might want to have some more sophisticated tools that deal specifically with these types of errors. And so our idea here is to catch errors without running the code, maybe even before we compile it. Let's see if this is possible. There are other tools as well that detect errors while the code is running, that modify the code as it's going and attempt to catch things before they go really wrong. So here I have a program, bad.c, that does a lot of the bad things that we've been talking about. It doesn't have freeze, it's got a whole bunch of bugs. So up the top, we have an example of a memory leak. So we malloc 10 bytes for the string hello. It's not a problem that the string is smaller, that the string hello is smaller than 10 bytes. Sometimes we know we allocate more memory. What is the problem there? What have I forgotten to do? Bell. At the very top, I've allocated 10 bytes of memory. I've copied something into it. I printed something with it. What have I forgotten to do after? What do I have to do after every malloc once I've finished with the memory? Free. Yeah, so I don't have a free there. I've just forgotten. Okay, what about the next one? What have I done here, Ahmed? So I have created a character array, I put some stuff in it, I've freed it, and then I've printed after I've already freed the memory. So I no longer have permission to use the memory, but I've used it anyway. Max, what about this one over here?
I'm going to guess that it's an out-of-bounds access.
Well, it does say that in the comment, but give me a little more explanation.
You're going to number 5 and you've only got 4, index 4.
Yeah, I've only got index 4, so index 5 doesn't exist. And it's an array of 5 elements, which means 0, 1, 2, 3, 4. So if I try and access number 5, because you see there I have an equals to, my program is going to again be accessing memory that doesn't belong to me. And then Kelly Rowe, the last one over here. Yeah, my integer is too big, it doesn't fit. I've gone one more than the max integer. So this is a pretty bad program. I really regret writing this. So let's run it and see if it runs. So here I have bad.c. Now what I'm going to do is I'm going to run clang, my compiler, but I'm going to give it some extra flags. That should be an equals. There we go. So I will post, these flags will be in the slides so you can check it out. And then I'm going to give it a run. Oh, it printed out some stuff that wasn't in my code. What's this done? Okay, let's look. Okay, error. Address sanitizer, heap use after free on address whatever. Okay, now let's look at a version that I prepared earlier of it with some stuff highlighted. So it seemed to identify that there was a bug in my code, giving the compiler additional flags. And what it actually did is it added some extra code into my code when it compiled it, so then when it's run, it can detect some of these things. So this is a form of dynamic analysis. So we'll see heap use after free. There's a read of size 2 that I shouldn't have done at bad C line 12. And you can see it also gives us where it was first allocated and where it was freed. So what I've done is I've used memory that I've already freed. Where did I make that memory? At line 6. And where did I free that memory? At line 11. And where did I use that memory? At line 12. So this is quite a powerful tool for you to use to start detecting errors in your code. The other program you can use is one called leaks, which I probably don't need to demo this live, but you can see here I've used another program on Mac. This one's only on Mac, called leaks, and I've given it these arguments, and there you can see that it has found the memory leak inside bad because it's given me this error report over here. Now the problem with the leaks program is the output can be a little hard to read, so I would, it might be easier for you to use this to at least find some of the bugs than this program, but it can at least help you identify that there is a memory leak, because you know if you see this output, then you've done something wrong. If you're on Windows or on Linux, then we do have another tool that's also quite useful. This is called valgrind. And it might be a little hard to see. We'll see if it works anyway. So this is on Ed. So it produces all of the output after running bad. And then we can see a whole bunch of invalid reads. So it tells you where it was allocated. It gives us a whole bunch of other bugs that it's found. It's found use of uninitialized value, so where we have used something that we haven't allocated yet. Remember, we had that out of bounds access. And it also tells us about the memory leak at the bottom over there. So valgrind is quite a powerful tool for doing this, with the catch that, oh, where are my lights? There we go. With the catch that valgrind does not work at all on M1 or M2 Macs, any of the new Macs. It doesn't work, and it's probably not going to work for the foreseeable future. So valgrind was a great tool. I would also encourage you to try out the leaks tool if you're on a Mac, and the sanitize address flag. Of course, Clang has a whole bunch of other flags that can also detect things like integer overflows, and we'll get to a bit of those later. So thank you very much, and I will see you all tomorrow.